I promise I'll try to make this entertaining, since it's the last talk. But you'll see in the background there's some ramen there. And you're going to be like, oh my God, Vincent, what the hell has ramen got to do with anything around AI? Also, you think. So I'll make it interesting. We're going to talk about prompt optimization, but I'm going to use ramen as a vehicle for this example. And when we talk a lot about research topics, things like optimization and algorithms and things, it can get a bit confusing. So it's good to ground ourselves with something delicious, such as food. I might make you hungry. And these are some of my ramen picks, actually. So I'm Vincent. I had a quick intro. I've worked for a number of companies. I coined myself a futurist. It's a self-proclaimed term. I don't think I've met anyone that's been called a futurist by anyone else. And you can see on the right, there's Oculus Rift goggles. This was like one of the alpha versions. I think it was like 15-something years ago. Who would have believed that even VR was a thing? But I was putting this thing on my face. It came with a warning saying, don't wear it for more than a minute. I wore it for 2 hours. I vomited profusely thereafter. So technology, same as AI and anything else we're seeing, is experimental. It's different. It's fun. It doesn't work half the time, but we have to keep trying and we have to keep experimenting. And it's that experimentation process that sometimes leads us to something interesting. I'm going to touch on Opik and Comet just 2 seconds, but that's not the focus on my talk today. So Opik is an observability platform, and if you want to find out anything about what we're doing, feel free to come and speak to us downstairs. The team are downstairs, I'm downstairs, or grab me afterwards. But the part that I'm excited about is how we go from evaluation and telemetry to action. So if we're capturing telemetry and we're capturing what's happening inside your AI application, like to me, it just didn't make sense that we couldn't do anything with that, right? Like we should take action, we should fix the problem rather than telling you, by the way, you have a problem. I mean, we're at a point now with like these IDEs like Cursor and other tools like that, that we can suddenly get to a point where, oh, I see that this is happening, I'm gonna do X, Y, and Z. To me, this X, Y, and Z seemed like a simple thing to do, but as I went down that rabbit hole, it got a little bit more complicated. And to me, this analogy, I think this analogy, someone can tell me the history behind this. It goes back many, many years, but it kind of touches on this like impossible triangle is the best way I can describe it. And I kind of put these 3 pillars and tie that back to LLM. So you have speed, cost, and accuracy. And when we're going to build anything, right? You're going to build a house, you're going to cook ramen, whatever. You can have it quick, you can have it cheap, but you're going to lose out on accuracy. So you got to just imagine there's a pinpoint somewhere along that triangle. Something is a trade-off with something else. And our journey into large language models and the way we started somewhat ended up in this space as well. You know, we started off with prompt engineering, which was as soon as like these LLMs came out, it became this sort of term that we bucket ourselves into. We went into the world of context engineering, as one of my colleagues at Red Panda earlier kind of pointed out that, you know, RAG is not a new concept. This thing of context engineering has been around for quite some time. And then we're kind of going into this world that I like to call intent engineering, and I'll kind of touch on that a little bit because when I look at prompts and the way we've been doing prompts at the start, I kind of use this wording of like doom wordsmithing. We're essentially taking words and we're bashing it into an LLM, like, you must do this. If you don't do this, I'm going to lose my job. You're going to lose your job too. Someone's going to die. And it's just like this, like, words to like to try and force this model to conform and behave in a certain way. Kind of felt like it made sense a few years ago, but the more I look at it, it just seemed like utter nonsense. But for some weird reason, it somewhat worked and got us somewhere. So you had these like people that had worked out this magic flavor of tokens, so to speak, like a secret sauce, like the KFC recipe almost in a way to LLMs. And that was kind of getting us somewhere there, but not quite there. And then we kind of landed into this world of context engineering. We're like, well, we can't solve this accuracy hallucination problem. What the hell are we going to do about it? Well, it was like, well, we can bring some context, we can bring some memory into these models and give it some start. But we're still stuck in this paradigm of the input as the starting point and then the hopes that it leads us to the output. And that's why I'm coining this like intent engineering. Someone's got a better wording for this, by all means, like go for it. But I had to put it in a placeholder to kind of explain this concept. And I think optimization kind of sits in this bucket, fine-tuning to a degree. There's going to be other forms of this, but it's really, I want to start with the output. I want to define the output and work backwards. Let's say I'm a PM in an enterprise company. I should be able to like define what my expected outcome is, see some examples, create a golden data set, and then that's the starting point. And if it doesn't match that expectation, there's a failure and there's like a score attached to that, or I know where it's going wrong. Right now, it's like I tell someone to write a prompt and they go off and do this whole horrid process. And it's back to front. So I think we need to flip it on its head to actually get us to a point where the model works for you in your given context, and we have a bit more clarity around what that actually means. So we start with the agent. It's just a really simplified view, but like even when we look at the agent, there's many components to it. So when I talk about optimization, I'm going to talk about one of the components, but as you can see, there's multiple facets to this thing, or you might even in some cases have multiple agents. So then, okay, how does this work in combination with each other? So keeping it simple, you have an input with some data set that's going in, which could explain what's going on, and that's going to create the user and system prompt with that input. In the middle layer, you've got some tool function. I mean, an agent could just be a prompt, but in reality, it's going to have some ability to take action. It could be function calling, it could be writing messages. You define whatever it is. And then you've got like the base, which is the inference, which is the model itself, as well as the parameters that come with that model. So one way of optimizing could be finding a faster model at a price that makes sense to you, right? Like, which is a logical step you can do. Like, you may not have to change the instruction, or you can fine-tune the model or find a better model, right? So you kind of start off in this prompt engineering journey where you go, I'm getting some output, and then you're going, well, why is this model hallucinating? Let me try to fix that. And then you just kind of vibe check it, and you're like, I'm going to bash some words into this thing and hopefully create a better prompt. And that's flawed. And it's flawed for the same reasons I spoke about before, because it's missing that signal, the triangle. Like, we don't know if this thing is kind of heading in that right direction and it's kind of making sense whatsoever. But if we say, let me write this better, but let me test this and kind of build a bit of structure around it, that's when you're actually starting to get into some sort of systematic approach to prompt engineering. And funny enough, I still know companies that are doing this, that are enterprises and have smart people on their teams, when the leap to this is like very small, but the delta in the improvement is massive. I think there's a fear that, they're going to realize that maybe the prompts they were writing were not working or not useful. But same as in machine learning, we define the measure of success, the speed, the accuracy, the latency, whatever, and we test against that. I'm not advocating for you to use Opik to solve this. You can, it's open source, you can get started for free. But like even an Excel spreadsheet and even a simple way to just validate and have a test case to say, is this working every time, is a way to start on that. And congratulations, you've kind of reached level 1. We've got some noodle on the plate, we've get something out of a model. It looks a bit bland, but at least the machine's working, like we're getting an output that's sort of conforming to what we want. But we then sort of went along this journey and we're like, look, we've got the noodle, but it's still not quite right. Like it doesn't match my flavor and taste, it's super generic. Like it's hallucinating, it's not what I expected. And it's really taken us like a couple years of research. And the big sort of shift that happened was essentially this concept of meta prompting, and which kind of led to a lot of some of the stuff you're seeing around chain of thought and reasoning models and things like that as well. But the short answer of the research was yes, we can actually use an LLM to do this task for us. So the part that I just showed you, maybe an LLM could write the prompt, we can test that, and we can keep doing this loop over and over again. So our version of a meta prompter does something similar to this. It takes the prompt, creates a version of the prompt, multiple versions for a better word, tests them, learns from that, and keeps iterating on that loop until we get an outcome. Now, you could do this yourself with just an LLM and a couple loops and just keep doing it, right? Like, it's not a complex process. There are some other tricks and stuff you can put under the hood, but in essence, this is like a very simple, basic optimization methodology you can use. So in this case, the chef looks at the recipe and says, I can write a better one, but also is kind of doing all the work itself. So a better sort of way to look at this is that, you've got this like Michelin star dish, ramen or whatever, with all the ingredients that you've never seen before, and you've been told to cook. And it's kind of true of LLMs. If you're getting an LLM to write the prompt for you and it hasn't seen this thing before, it's just going to create lots of things. It doesn't mean those things are going to be any good. What we're doing is we're creating more trials, more versions of prompts, and we're just hoping that one of them are going to strike gold. And 9 times out of 10, if you do it hard enough, long enough, with enough context, you will. Or this thing has some domain knowledge in the LLM, so maybe it's been exposed to prompts before, a data set. So it has an idea of how your thing works. It's a good starting point, right? So this works, but it only gets us so far. You know, we get stuck. The ramen still comes out. Maybe it looks a little bit better, but you just end up with lots of different ramen. So in this case, you've kind of reached level 2. Yes, you've got a better prompt, sort of, hopefully, but at the same time, it's not exactly what you need. You just got lucky by creating a million different versions of prompts, the one that kind of got you closer to what you're looking for. It wasn't precision. It's kind of like me kind of coming up with lots of drugs and medicine and just giving them to lots of people and saying a lot of people got cured, which is kind of a little bit how medicine kind of works with this trial and error thing, but it's not precision. It's not designed for that specific individual mind. It's designed for a group of people in a given scenario. And that's kind of what's happening here with the prompt engineering in its nascent stages, where we kind of started off. But there's alternatives to this brute forcing methodology. And apologies, I'm going a little bit fast. I'll have time for questions at the end. Like, I'm trying to cover a lot of these topics in a short space of time. But yeah, there are alternatives to this methodology as well. So we can get smarter about pinpointing the exact mechanics of what is happening without having to go through that like constant, like just getting the machine to carry out words. And there's a bunch of other optimizers that came before these. But some of the ones, 2 of the ones I'm going to highlight are our own. And one of the ones is the GEPA one, if you've heard from DSPY. The GEPA one and the one we wrote in April uses sort of a genetic methodology, which I'll talk to in a little bit. And I'm also going to touch on the other method, which is kind of using like a retrospective, I would call it. I may or may not have time to go into GEPA, but I'll kind of touch on the examples. So this new wave has kind of emerged in the last sort of 6 months or so, where we're starting to see that like these things can like genuinely do some like real serious work and create prompts of like pretty decent value that can sometimes like rival prompt engineering in some organizations or in some use cases as well. So a quick touch on like genetic algorithms. Essentially on the left is the example, let's just say the meta prompting, where we're starting with the prompt at the top, here the system prompt. We take that system prompt out and we say, hey, we're going to create like 10 variations. And we find this one here is working really well for us. And then we go down, we take that and we create another 10 variations based off that one as the seed, and we go down. So this is what we've been doing with like the meta prompting example that I touched on. But when we talk about genetic algorithms, it's literally what you would think. When you think about or evolutionary, different people use the different term interchangeably. You have this concept where you take the prompt, but in this case, you create that prompt has children, right? So you're going to end up with like multiple people, and people are prompts in this case, and a population. So the population at the top might be a population of 5. But what we're then going to do is we're going to mix these children together. They're going to grow older, they're going to mutate, their genetics are going to mutate. We're going to change little parts of their prompt so they're not all exactly the same. And they're going to have children of their own. So we're going to find that 2 prompts worked really well. What happens if they have a child, like we join them together, and they have children? So it kind of gets down this like really interesting rabbit hole of like learning and modifying and changing, which is very similar to some of the concepts you see in like reinforcement learning, but applying that concept to prompts. This is a really simplified view of what's happening, but imagine you've got like a population of 50 and you've got like 1,000 or 2,000, 3,000 trials that are happening, and you end up with a prompt at the end, which is like some weird combination of like all these learnings that have happened over years, so to speak, within a sort of prompt speak. So the evolutionary optimizers sort of follow a similar pattern, but instead of going in and saying, hey, we're going to just take the prompt and the population and just create prompts, what we're doing is we're mutating them and we're merging these little components of prompts together, making different versions, evaluating them, and then going back to the start. But the difference in this case is as we go through each evolution, we kind of do this concept, at least in our optimizer, called a Hall of Fame. And that kind of works a little bit like a census is probably a better analogy in this case, of like we're basically jotting down what worked, what didn't, and where's the population at, and what was the winning thing. So in this case, like what was the biggest, most important job, or what was the most used name in that time of year, right? So we're kind of keeping a record of like what's happened, and that record is what's informing this optimizer at the top to then come up with new prompts. We're also doing other tricks like snipping top and bottom and things like that, which are very similar to like in ML, where you don't want to reach like a same point every single time. We want to inject a bit of randomness into it. So going back to the ramen example in this case, you're going to have multiple ramen chefs essentially competing against each other, and the best dish will evolve, and the losers go home. If anyone's watched MasterChef or anything along those lines, or any of these like cooking programs, it's essentially what we're doing in this case, where we're maintaining that population, and we're going around. There's other couple tricks that we've deployed where we've got like a cold start problem, or a problem where we might converge into the same prompt all the time. So every so often we might re-inject the starting prompt back into the population, or we might take the data set without looking at the prompt and ask the LLM to create a prompt based on this data set and inject that back into the population. This is very similar to like events that will happen in the real world where, I don't know, there's like a pandemic or a disease or different things happen that will change like the course of action. So we're kind of bringing in that level of randomness into this case. GEPA is very similar to this approach. The only difference with GEPA, there's quite a few differences, but the main one here is that instead of doing population in the sense of I'm going to change the entire prompt, the prompt gets chopped up into pieces like ingredients instead of the entire dish. We're changing the ingredients, and we're mutating the ingredients, and we're stitching those ingredients together and seeing what works. So it takes a kind of similar-ish process with some other kind of differences to that. And it has a scorecard, which is called like a Pareto function, which looks at the relationship between that triangle that I spoke about, the cost, the accuracy, and stuff like that. So you might end up with a prompt, ideally, that isn't like bloated with lots and lots of tokens, and it's trying to balance out the needs. So if accuracy is quite similar, it might preference something that's maybe a shorter prompt instead of a larger one. So that's kind of the very kind of the nuanced difference between the two, but they kind of behave in a similar way. So in this case, as I mentioned, we break that dish down into its components. So in the ramen, there's like the noodle, there's the broth, there's the oil, there's a spice. So you're working on those pieces and optimizing those pieces and then reassembling those dishes together to come up with like a new variation of a prompt instead of going, I'm going to build entire dishes all together and mutate parts of that dish as a difference. Now, where we changed this approach entirely and we decided, look, this is kind of working, what we tend to find, and the research on this is, we're still going to be publishing this pretty soon, is these work great in like an example where you've got like a research data set of Hugging Face and you load it in and you give it a go and you're like, wow, this is great. But in reality, prompts are more complex in organizations. Like you take one company and their prompt is maybe like 20,000 token lines long, right? You've already reached that like maxing yourself out with that like prompt engineering work that you've done. Then where do you go from that? Like you try and put it in someone like this, it's not gonna do well because it's always designed to start with some smaller base and then add to it and subtract to it and grow. And the more we started thinking about this internally, the more we started thinking like, actually, if I was a prompt engineer and I was facing this problem, how might I think about it? Like, how do you think about a problem which you may have no idea about? And it's really kind of simple. It kind of boils down to what we call like root cause analysis. So in this case, our next optimizer, this was very recent, only like released like maybe a month and a half ago, called HAPO, which is Hierarchical Adaptive Prompt Optimizer, essentially starts with a failure. This is kind of going into that intent engineering world that I was touching on, where we're actually going back to front and we're going, hey, we looked at this prompt and we ran it and something went wrong. So in this case, it could be a very simple piece of code maybe that runs, but something about that code means the accuracy doesn't work quite right. And I'm going to show you an example where we've applied this into production. And we look at that and we go, okay, we're going to come up with 5 reasons why we think this has failed. Imagine you've got 5 top engineers in front of you, go, you, A, what went wrong? B, person, what went wrong? And they might say something like, oh, the syntax was wrong. You used the wrong package. The way the class was defined could be a little X, Y, and Z. So you come up with these strategies, or you group these strategies based on the failures. And you take these failures, you group them, and you come up with strategies. And those strategies become new mutations on the prompts. You apply that to the prompt. You create an evaluation process, and you reflect on that evaluation. You go, okay, we reran this. This was the new score. But actually, we found out you fixed this one little thing a little bit better, I think, but these other areas are still a failure point. So we keep going, asking why, looping through, and we find that this takes you in a completely different pathway from some of the other optimizers and the way they approach it. And kind of going back to that food example, you don't know what good tastes like. You might not know. Like, you may not have tested best dish, or you may not have tasted, had listened to the most, you've been in a sports supercar or something like that. So you might not have experienced that. Like the model may not have experienced the thing that we're looking for, but it's within its realm of possibilities in a search space. So taking a dish example, it's like I taste the dish. I might not be the perfect chef, but I can tell you that maybe it feels a little salty. Maybe the texture's off. I'm just kind of listing out things that I think could be going wrong in this example, and then just tweaking it to see what happens. And taking all of these sort of like failure modes and grouping them together, we find kind of leads us into this sort of really interesting space. Just realized I've got the wrong 2 seconds. I'm going to change. So with this one, I was explaining like we go through that reflective process, and essentially it's similar to like a doctor diagnosing symptoms, prescribing targeted medication. We get an idea, we see the output, we kind of revolve, and we do that again. And an example of where we've managed to get this into the wild, and this is something we're going to do more of, and if you have suggestions, let us know, is we tried a couple of different methods, and we've posted this up. You can check the link in the bottom in our repo, which might be hard to see, but we'll make sure we send it around. Is LangChain has a JSON mode. So if you've ever worked with like open source models, you're trying to create JSON mode, they have like a function you can use. And I met people that are like, this thing keeps failing all the time. Can you please, for the love of God, like prove your apple's worth and just go and apply this optimizer in this case? So we applied it here. It ran for a number of iterations. We used a number of different optimizers. So we tested the one that gave us the best result. In this case, it's gone from 0.12, so like a 12% baseline of like 100% accuracy all the time, 2 times out of 10. And we got it to like a 97% accuracy, which is like a 700% improvement on this particular prompt. And you could see we're just explaining what to do with the JSON. And the data set's all public. We're using examples of JSON data sets we found on Hugging Face, and we're using this reflective process to come up with a better prompt, and then we're applying that back. So we wanted to find examples in the wild that we can test this in like live use cases. We've got a number of other similar ones that are coming up. But if you see any like multi-agent systems and prompts that are in open source, or if any of your products or services are open source and you have prompts available, I'd be more than happy to have a crack at optimizing that for you and applying that optimization back into your organization's code base. So here, congratulations, we've reached level 3. We finally have something that kind of resembles ramen, because you can see here that we're actually getting the JSON output that we're looking for. Now, we are going to get optimizers that are going to get more and more complex. Things are going to get a little bit more interesting. And I think the key takeaway for me here is that like there's going to be other forms. Like, you remember that pie that I showed you? What happens when you have multiple agents? What happens when you have tool calling and things like that? So we've been looking into that as well. So we've got like optimization for MCP and function calling. We've been looking at like that kind of different strategies of how do we sort of tackle that. But I think the key thing here is to experiment, right? Like taste things, try it, give it a go, and see if it's right for you. Like if you're starting with the prompt and you're struggling, like what does prompt engineering look like? In my opinion, prompt engineering has shifted. I hate to use the word it's dead, but it's dead in the old way of how we know it, of like just bashing words into a machine and making sure that works. And leverage them for your projects. And like another good way of example of thinking about it, as I mentioned, is like start to think about how you define your prompts internally currently in your organizations. What does your prompts life cycle look like? And is a future change where optimizers become more current, is that going to change the way you think about it? Like a year and a half ago, we had people's jobs that were like prompt optimizers, right? They were hired to do this specific job. So have a think about that. So you've got the access to the docs on the right, and then my LinkedIn on the middle. I'll welcome questions, but I will add that all of this work that has been done is open source. The entire code base, all the optimizers I've walked you through, is publicly available. And we have a number of announcements around the benchmarks and some of the methodologies that are going to be coming out over the next few days and weeks as well. Thank you.
Vincent. Thank you, Vincent. We are opening up the floor for questions for Vincent. Anybody has questions? No? Oh, I see. Okay.
Hey, hi, thank you. It's a great talk. I guess my question is mostly around how do you measure this accuracy, and how do you make sure that it's specific to the domain that the prompt is curated for?
Yeah, good question. So if we go back to some of these earlier slides, let me find this. Like if we go back to this really simple loop, right? You've got the data set which then informs the input. So without a good curated data set, your optimization fails. And we go back to the same thing with anything in AI. Like it starts back at that data set. You need to define a really clear data set that kind of has good examples and bad, which I'll touch on super quickly, but also the metric. Like what do you define as success? Is it accuracy? Is it hallucination? Is it cost? Like that triangle that I spoke about is like one part of it, but like being really clear on that. And that's where the Opik side of our platform, which does the evals, comes in, because we have like close to 30 different sort of evaluations out of the box that you can plug into. So maybe that's your starting point. But when it comes to data sets, if you're like, oh my God, like human data set, I'm not going to sit there and write 1,000 examples. Maybe you take existing traces of your application, you export that, and you use that as a starting point. You get a human to annotate it, or an LLM to evaluate good and bad, and you start there. Or you just synthetically do half and half, or you use traces and get an LLM to create more examples of that, and then you annotate it. But there's like a bit of a workflow needed to like kind of create a baseline of examples. But we found on another paper I published, is like something like 20 to 30 examples can give a signal to an LLM. If it's not, it might not be the best signal, but it's still a signal. So like, don't feel like there's a massive amount of data needed to make this work, but obviously more data means better confidence, means better outcomes, and likely higher accuracy readings. Because if you're trying to score something with 5 examples or 10 examples, you're not going to get a good read on if this is going to work well all the time.
Thank you.
Thank you. Question? Somebody's up. Oh.
Thank you. Would you say that this is sort of like doing hyperparameter tuning, but instead of with parameters, you're doing it on the prompts?
Yeah, essentially. The only difference with hyperparameter tuning, you tend to have an idea of what the search space looks like in a loosely defined way. Like you kind of know what you're looking for. You just need a smarter way of getting there. In this case, the search space is somewhat near to more infinite than a hyperparameter tuning. So it becomes more complex to like find. It's like looking for a needle on Earth rather than like a needle in a room where you can just go through every single dot with your eyes and work your way. Or maybe you could be smarter about how you scan, which is essentially what hyperparameter tuning is. Does that analogy give a bit more context to like, yeah.
So this is pretty cool and new. So I guess the question that sort of bugs my mind is, do you have any real-world cases that you can share where using your optimization actually ended up resulting in improvement? You don't have to share the names and so on, but it would be nice to know.
Yeah, so the one I've shared was the LangChain one, which I've myself personally done, and then committed back to LangChain, and then within a couple of hours it was merged. Surprise. But some of the other use cases that we're looking at, and without talking about customers, I'll give two examples. The first one is when we think about the process of when you create an LLM as a judge, where an LLM is creating and looking at the input data coming from another LLM and scoring it, that's a prompt as well. So one use case that we're looking at is like, okay, if you've annotated your data set, could I take that annotation data that you've annotated your traces on in terms of what's coming out of your AI and actually not fine-tune, but like instruction tune your LLM as a judge to like make the judge prompt better and actually have an accuracy attached to that. So now suddenly we go from like, is LLMs any good at judging my work, to like LLMs are good at judging my work with a degree of confidence of X and Y. So that's like a very proven sort of pattern that we can follow. We've got some more extreme use cases. Like we've got one company we're working with, which is like a large media company on a POC. And I've been working on multimodal evals as well. So we've got like video-based LLM as a judge. That's like a whole nother conversation in itself. And what we're doing is, because our evals support it, so does our optimizers. So we're kind of getting to this space where like I've got an agent that the data set input is an image or a video instead of text, and I want to create a better classification. Like I might be looking at safety risk or is this person an influencer or not? Or is there any children in this video? Things like that, right? Where you just want to use an LLM to do that, like a vision-based LLM, instead of like kind of doing computer vision stuff, which is as good, but it just takes time to set up. Yeah.
Right, cool.
Thank you.
Yep. Anybody else have questions? Can't see. No? Oh.
Okay, just a question. How you can compare Opik efficiency with DSPY prompt optimization?
Yeah, so when you're talking about the efficiency, DSPY is for some of you that do know or don't know, is an agentic framework. DSPY first released the MiPro with like one of the optimizers that was like in the earlier list of like optimizers that kind of really started this race. And the issue is probably not so much the issue if you love DSPY, but it relied on DSPY as a framework. When we built this optimization package, we took the MiPro algorithm out of DSPY and we used that as our starting base because we needed something that didn't rely on like a framework and was totally agnostic. You can use any LLM you want, you can use any framework or agent you want. Since then, they've done a lot of work, and not DSPY, but the team behind DSPY, who are researchers at like Berkeley and Stanford and a few of the people at Databricks, have then subsequently built GEPA, or just, you know, partially. It's a sub-project of DSPY, but it doesn't rely on DSPY. So I think there's a lot of misconception in this space that like DSPY is an optimizer. I think there are optimizers within DSPY, which is what's making DSPY really popular. But we also give you those same optimizers agnostic of DSPY. So you can run those same optimizers in our SDK, but we also have our own optimizers as well. And they behave differently given different scenarios, given data sets. I don't want to share just now because we're still going through the benchmarking process and we'll be publishing results. But depends on your use case and the data set and domain. Like each optimizer has its different quirks and they provide different results.
Great. More question? More question? No? Okay. I don't think I'm missing anybody else. But Vincent's still here if you want to ask him question outside of this room as well. So
thank you so much.
Thank you. Thank you so much, Vincent. So wonderful. Yep.